All right, hey everybody. Today we're going to be talking about exponential derivatives. This is one of the coolest things for sure in derivative calculus that we have, and so I hope that you watch and enjoy. There are going to be some proofs in here. If you don't want to watch the proofs, not the biggest deal, but make sure you catch the summary at the end for the derivatives that we're going to talk about in this video. So students will be able to find derivatives of exponential functions with e and any base. So let's take a look. So, chain rule we're going to have to talk about. We've been talking about it in every video. Logarithms, exponential function, and log rules are also going to come into play in this one. So, first we're going to try some bell work with some of our newfound general inverse function properties. So if you want to give this a shot and then come back, let me know. All right, let's give this a try. So, f of negative 1, if I want to find f of negative 1, I just have to go right here. It's 0. And f inverse of 1. So this is interesting. F inverse of 1, I'm looking for 1 this time in the y values. I'm looking for 1 in the y values because that's going to tell me, remember, some number 1 is on f, so that means that some number is on f inverse. So I'm looking for that, that number that corresponds with a y value of 1. Looks like that's negative 2. Okay. Love table problems. Free points. Equation for the line tangent to f of x at x equals 2. So when x is 2, I need a point and a slope. Point is going to be 2, and it looks like negative 5. And the slope is going to be f prime of 2, which is negative 2. So we have y plus 5 equals negative 2 times x minus 2. Easy peasy. All right, now the derivative of the inverse evaluated at x equals 0. So this is where I'm going to make that little table thing. So I got some point on f and some point on f inverse. I want the x-coordinate of f inverse to be 0. That means that's got to be the y-coordinate of f. So we're looking for 0 in the middle here. Looks like that's negative 1. So that means negative 1 is here. And we want to know the derivative of that guy. Well, I don't know the derivative of f inverse, but I know the derivative of f at negative 1. So that is... looks like negative 2. So that means f inverse has the reciprocal slope at the buddy point, which is negative 1/2. Yep, so that is our derivative at x equals 0. All right, so now they want the equation for the normal line to this guy. So we need a point. So we have negative 2, f inverse of negative 2. So we're going to do our little chart here. So I want negative 2 to be the x for the f inverse. That means negative 2 has to be the y for f. So I'm looking for the y in here. It looks like that's 0, negative 2. So this is negative 2, 0. And so we got our point, negative 2, 0. And the slope is going to be the derivative here. So I can find the derivative of the regular function at 0, negative 2. That is negative 1. So this is going to be reciprocal, which is still negative 1, right? Because 1 over negative 1 is negative 1. So we got y minus 0 is negative 1 times x plus 2. Nice. All right, let's jump in. So this guy is Leonhard Euler. Leonhard Euler, E-U-L-E-R, not Euler. It's pronounced Euler. And he did a lot of great things for mathematics. And one of them was doing a lot of stuff with the development of geometry and non-Euclidean geometry. And he also has this great number named after him. He dealt with this number a lot. I'm guessing he did not name the number after himself, but I'm not sure. You could look that up and see where it came from. But Euler's number is E. And E is defined as the limit as n approaches infinity. Infinity. That's an N, not an H. Write better here, of 1 plus 1 over n to the nth power. Now, this is kind of a weird thing, because when you look at this, you think, well, n is becoming infinity, so this thing's getting really close to 0, and this thing's getting really, really big. So if the problem is you have 1 plus something getting really close to 0, but it's not quite 1. It's small, like this part's small, so it's not quite 1, and then this guy's getting really big, so it's like a competition. Is this going to turn into 1 faster, or is this going to get to infinity faster? Because if this gets to infinity really fast, the whole thing's going to blow up. And if this gets to 0 really fast, then 1 to any power is just 1. And the really unique thing happens. This ends up being a number. It's 2.718281828459045. It goes on forever. kind of like pi. It's an irrational number. And it's just weird because this limit where you're playing tug of war ends up kind of meeting somewhere that is unexpected. And this number comes up all the time in nature and in math and all kinds of stuff. So this is Euler's number. It's defined as this guy right here. And what we're going to do now is we're going to come up with a lemma that we're going to use in the next proof. Now, of course, once again, I am being magical and knowing we're going to need this. But we're going to try to prove that the limit as h approaches 0 of e to the h minus 1 divided by h is equal to 1. So we're going to try to prove this using a lemma. And of course, this is a proof hat. And you know, this is a proof hat proof. This hat that Euler's got going on, I'm not the biggest fan of it. So let's see if we can get him a little bit more styling. There we go. He's got his proof hat on now, so he's going to do the proof with us. So if we plug in 0, we get 1 minus 1 over 0, which is 0 or 0. No big surprise there. That's what happens with all these limits. What I'm going to do here is I'm going to use our definition of e to try to get this idea, to figure out this limit. So what I'm going to do here is I'm going to borrow this for a second, and I'm going to say let h equal 1 over n. So h is going to be 1 over n. So then this becomes e is equal to the limit. So if h is 1 over n, as n goes to infinity, h is turning into 0. So we can do that, right? If n is coming in infinity, h is turning into 0. So we have this limit as h approaches 0. So this is going to be 1 plus 1 over n is now going to be h. And then our exponent, instead of being n, well, if I want to solve this for n, I can just do the swap property, swap the h and the n. I'm multiplying by n both sides and dividing both sides by h. So n is equal to 1 over h. So this is 1 over h power. Now what I'm going to do is take e to the h for both sides. So I'm going to take both sides to the h power. So we have limit as h approaches 0, 1 plus h to the h over h, which is just limit as h approaches 0 of 1 plus h, because that's to the first power. Okay, so what I'm going to do now is I'm going to replace the e to the h right here with this guy, because I just found that e to the h is limit as h approaches 0 of 1 plus h, so I have the limit as h approaches 0, so I can just replace it. So I have limit as h approaches 0, e to the h is now 1 plus h, minus 1 divided by h. Well, 1 plus h minus 1, 1 minus 1 is nothing, so I have the limit as h approaches 0 of h over h, which is 1. So we've proved this little lemma. We're going to use this now to find the derivative of e to the x. So let's give it a shot. So we're going to come back. We're going to use this little nugget here. So derivative of e to the x from limits. So limit definition of derivative. Limit as h approaches 0, f of x plus h minus f of x divided by h. I'm interested in the derivative of e to the x. So that's going to be limit as h approaches 0, e to the power x plus h minus e to the x divided by h. So first thing we're going to do here is we're going to use some of our exponent properties to be able to split this up, right? So all I did was plug x plus h into here, but that sum of exponents I can split up. That's the limit as h approaches 0, e to the x times e to the h minus e to the x over h. Now we can factor out an e to the x. So I'm going to pull it all the way out to the front, because there's no h there, so I can just pull it out. There's no h, doesn't depend on h. So we have e to the h minus 1 over h. Ooh, that sounds familiar. Is that something we've seen before? Yeah, that limit is 1. So this is equal to e to the x times 1, which is e to the x. Well, hold on a second. I was finding the derivative of e to the x. It equals e to the x. Does that make any sense? Let's look at a graph. So here we have e to the x. I draft it in Desmos. So what they're saying is the slope of e to the x, like at this point right here. So the slope there, they're saying is equal to the value of the function. So the derivative of e to the x at 0 is e to the 0, which is equal to 1. Yeah, I'd buy that. Looks like it's 1. At this point right here, this is at 2. They're saying that the slope of this guy is e squared, which is the value of the function, right? E squared, like 3 squared-ish, well, 2 point something squared should be between 5 and 10 somewhere. That makes sense to me. And over here, like at negative 5, the slope of this thing should be e to the negative 5th, which is 1 over e to the 5th. So the value of the function is the slope. So if I told you, draw me the derivative of this graph, what would you draw? Same graph, right? And the derivative of that, and the derivative of that. The second, third, fourth, or fifth derivative, every derivative of e to the x Just the same function, e to the x. That is like the coolest thing ever, and I think someone else agrees. Crazy. Look at how crazy that is, right? So the y value of the graph is equal to the slope at any point. That is awesome. I love it. So let's see if we can do some problems with that. So derivative of e to the x is just e to the x. So if I'm doing derivative of e to the sine x, I have a baby function of sine x. So I'm going to leave that alone, take the derivative of e to the x. So that's just e to the x again. So it's e to the sine x multiplied by the derivative of the baby, which is cosine x. And that's it. So you leave the e part alone. Whatever it is, just leave it alone and then multiply by the derivative of the baby function. Pretty cool. Let's do this one. So that's going to be e to the 1 over x. Leave that alone. Multiplied by the derivative of 1 over x. That's x to the negative 1. So that's going to be negative x to the negative 2. Rewrite that as negative e to the 1 over x. Maybe over x squared like that. Cool. This one over here a little bit more involved. Let's see. E to the tan inverse of x squared. So I'm going to leave it alone. E to the tan inverse of x squared, multiplied by the derivative of this baby function. So tan inverse has a derivative of 1 over 1 plus x squared. So I'm going to replace that x squared with an x squared. So x squared squared, multiplied by the derivative of its baby, which is 2x. I'm just going to leave it like that. You can put this up here and make this x to the 4th, but I'm just going to leave it like that. Not too bad. Chain, 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 right? Don't forget to chain those baby functions. All right, so what if the base is an e, Mr. Fransky? I'm so glad you asked. That means we're going to need some logs. So why do we need logs? Because logs are the inverse of exponential functions. So remember this, if y equals a to the x, this is true if and only if log base a of y is equal to x. So this is what's called exponential form. This guy over here is called, this is exponential form. This guy over here is logarithmic form. It's just a different way of writing an exponent. If you had me for pre-calc, you learned about the snowman bump, right? The a comes over, it bumps the x up into the exponent. But these are equivalent statements. And what is really important here is that these are actually inverse functions of each other. They're inverse functions of each other because log undoes an exponent. Right, if you take log base a of both sides, log base a of y equals log base a of a to the x. The question over here on the right is what power do I have to take a to get a to the x? Well, the answer to that is x, right? So log base a of a to the x undoes itself. It makes an x, okay? So inverse functions, not too bad. There's one special one. Ooh. The special log is the natural log of x. There's an e hiding there. Okay, you also might have seen log x before. Log x, there's a 10 hiding, but the e one is way more important, especially for calculus. So ln of x, the way I'm going to write this actually is a little bit different. Okay, so the way I'm going to write it is y equals, I'm not sure to write the whole thing. So y equals e to the x, if and only if ln of y is equal to x. Okay, so the e came over here. There's a hiding e right there. Okay, so logs and exponents are inverses. It's designed that way. Because exponents need an inverse function, so we develop logs to do it. Okay, so logs and exponents are inverses. And you might remember all of these log properties that I kind of showed off before when they were hiding. But if you have a log of a product, you can break it into addition. This all comes from rules for exponents. That's where these come from. The log base b of x over y is subtraction. Log base b of x to the n is n log base b. This comes from the product one, actually. So this x to the n, remember that means x times x times x times x times x. And we would have n of them. And then what the product rule says is you can change that into addition. So that'd be log x plus log x plus log x plus log x, and you would have n of those, and that's just multiplication, right? If you add n things together, it turns into multiplication. But the way people always think about this is just bring the exponent to the front. Log base b of b is 1, because that's b to the first power. Log base b of 1 is 0, because b to the 0 is 1. Log base b of b to the n, this is a useful one because it's like, well, what power do I have to raise b to get b to the n? Well, the answer to that is n, right? You put the b to the other side, you have b to the n equals b to the n. This last one is change of base. Change of base. Remember, the base goes in the basement. So the base ends up down here. Notice the b is new. There were no b's on the left side. right? We just had log base a of n. So you can choose whatever b you want. Generally, we're going to use natural log here. So you have ln of n divided by ln of a, because natural log is going to be really important for calculus. All right, so log properties, might want to Google some of that if you are a little rusty on them. Let's take a look here. So derivative of a to the x, using our new knowledge and a couple inverses. So what I want is the derivative, d dx, of a to the x. So right now I don't have a great way to do this. And what we're going to use is the fact that the natural log of e to the x is equal to x, right? Whatever is up here is just itself. Because the question is, what do I have to raise e to get e to the x? The answer is x. So I'm going to do this. Natural log of a to the, that goes the other way too, right? These are inverse functions, so you can do it the other way as well. E to the power natural log x is also equal to x. We're going to use this one to prove this derivative. Excuse me. So what we're going to do is, instead of just putting an x there, we're going to put a to the x there. So this is the same thing as doing the derivative of e to the power natural log of a to the x. So you might have to stare at that for a sec to make it make sense. A to the x is the same thing as e to the natural log of a to the x, because these are just inverse functions. They undo each other. So this would just be a to the x. Now we're going to use one of our properties, the one that I kind of showed a little proof of. The x is going to come to the front. So this is the derivative of e to the x times natural log of a. Now, the weird thing about that is natural log of a is just a number, right? A is just a number. Like, let's say this is the derivative of 5 to the x. So 5 to the x is the same as e to the natural log of 5 to the x. X comes to the front. That is e to the x ln 5. Ln 5 is just a number, right? It's a constant. So if we think about this, like if we're doing the derivative of e to the 2x, derivative of e to the 2x would be 2 times e to the 2x. Right? You leave the baby function alone, multiply by the derivative of the baby. There it is. So natural log of 5 is like that too. It's a number. So this is a constant times x. So the derivative there is just e to the x, leave that part alone, ln a, right? Leave the baby function alone, and then you multiply by the derivative of x ln a, which is ln of a. Because ln of a is just a constant, just like this 2 down here. And that is our derivative. But now I'm going to put this back into the form that we had it. E to the ln a to the x multiplied by ln a. So the derivative of a to the x is a to the x multiplied by natural log of a. Nice. All right, let's try some examples with that before we forget it. So derivative of 5 to the x, 5 to the x, ln 5. Just like that. That's all there is to it. This is not a chain rule. This is just the derivative of 5 to the x. Derivative of 3 to the cosine x, here we're going to have to use chain rule. So we leave 3 to the cosine x alone, multiplied by ln of 3. Now we chain, multiplied by the derivative of cosine, which is negative sine x. For what x value does f of x equals 3 to the x have a slope of 2? Well, let's see. So f prime of x would be 3 to the x times ln of 3. And we want to know when it's equal to 2. Okay, so that'd be 3 to the x is equal to 2 over ln 3. Now we have to get rid of that x. So we're going to take the log of both sides. I'm going to use natural log, doesn't really matter. So natural log of 3 to the x equal to natural log of 2 over ln 3. Now move that x to the front. So we have x ln 3 equal to ln of 2 over ln 3. Now we divide by ln 3 again. So x would be ln of 2 over ln 3 divided by ln 3. Kind of messy, but well, sometimes math is messy. Not a big deal. Nice. All right, so that's all I've got for you. So we've got Euler back here winking at us. I always thought that was kind of creepy. His right eye is always closed in all of his pictures. So summary, derivative of e to the x is e to the x. If you're doing the derivative of e to some function, then you leave that function alone, multiply by its derivative. And then the derivative of a to the x, you leave a to the x alone, multiply by the natural log of the number, which is going to be a constant. That's all I've got for you. I'll see you in the next video.